So last day, we looked at what are called many body problems, more than one mass. And my argument, Rachel, was actually I'll treat it like one big Ubermass. If they're attached by a rope or a string, we said they have to be accelerating at the same rate. We're not going to let you jerk on the rope. Das ist verboten. Instead, we're going to say, well, free body diagram, and then we're going to write an equation for all of the forces along the rope. And our equation is going to be winner minus loser equals the mass of all of them times A. In other words, to find the acceleration of everything, we're going to write an equation for everything. Then, to find individual forces, we'll look at individual masses. So, we even handled stuff with friction. I like example 4, I like example 4, I like example 4. And I gave you a bunch of questions to try. Question 7. I'm going to guess a lot of you got part A okay, but had trouble with part B maybe. So let's take a look at this. For part A, the trick, Sarah, is treat that as a 14 kilogram mass. And then it's exactly like some of the ones we did in the notes. You're going to have M1G, where M1 is 14. Normal force number 1, tension, M2G, tension. And so to get the acceleration, it's going to be M2G minus tension plus tension equals M all A. Why didn't M1G show up in this equation? It's not along the rope. And then we... losing tension. We would use Shea's theorem to get the acceleration. So it's going to be M2G divided by M all. It's going to be M28 times 9.8 divided by 2 plus 12 plus 8, the mass of all of them. And that's where the 3.6 comes, 3.56 and then 3.6 repeating, but that's where the 3.6 comes from. I'll store this on my calculator, though. Anybody get part B, the coefficient of friction? Yeah. I'm impressed, because usually almost no one gets it. What's the trick? Well, first of all, what's it a good job for? So I'm going to do a free body diagram on the 2 kilogram mass right here, because I have room right here. Here's the 2 kilogram mass. What are the forces on it? Get the obvious one. Okay. Is it sinking into the ground like quick? Is it flying into the air? So normal force. Which way, what direction is this 2 kilogram mass accelerating? To the? Which way do I have to have an unbalanced force then? To the, right? It's got to be a force that way. Question is, Donald, what is that force? Is it the rope? Is the rope touching the 2? It's not tension. What is that force? What? If this 12 was made out of ice, use your imagination. I think if that 12 was made out of ice and we yanked on the rope, it would yank right out from underneath the 2 and the 2 would just drop straight down. I think, yeah, I totally agree with you. I think friction is what's accelerating the 2. Not the 12, not the 8, but it's what's accelerating the 2 kilogram mass. That's your free body diagram. Who's winning? Friction. Who's losing? It's a trick question. And so you end up with now it wants the coefficient of friction, so I would go mu times the normal force. I don't know the normal force. Oh, but look. I would replace the normal force with mg. And then, Caden, you might notice it turns out here the m's actually cancel, and to get the mu by itself, I would just divide by g. If you didn't cancel out the m's, if you wrote it as ma over mg, you'll still get the same answer. But that's how you can find the coefficient of friction. Mu ends up being a divided by g, and if you wanted to, you could have left the m's there if you really wanted to, but same deal. You wanted the elevator one. Yeah. Let me emphasize, you're not going to get one as tricky as number 7 or number 12 on a Physics 11 test. Physics 12, I would have no problem as a multiple choice question. I always put one nasty multiple choice question, but not as a written. Okay. Allie, you tried this one. Did anybody get this one? Oh, nice. You tried this one? So let's follow it. By the way, the original question only asked that. It didn't walk you through A, B, C, and D, so it was really tough. Here, well, free body diagram, I'm going to do part A right here. What are the forces acting on the box? Get the obvious one. And? Which way is the box accelerating? Which way is the elevator accelerating? So which way is the box inside the elevator also accelerating? I'm just going to make sure I notice normal force is smaller. I'll exaggerate it. By the way, I think when it's talking about a scale, normal force. Okay. B says, draw a free body diagram on the elevator. I'll do that here. What are the forces acting on the elevator? Get the obvious one. An old trick in physics, if you have two masses and you're being lazy, if one of them is smaller, use a lowercase m. If one of them is way larger, use an uppercase M. So I'm going to use big MG as my elevator. Which way is it accelerating? Down. Is there something slowing it down, though? What? Yeah, no normal force. It's not sitting on a surface, but definitely friction. Okay. C says, what's the acceleration of the elevator? Well, I guess it's going to be big mg minus friction equals ma. Problem. I don't know that because I don't know mu. And I don't know that. I have what we say in physics or in math. I have an equation with two unknowns. Wait a minute. What's inside the elevator? A box. Will the box inside the elevator be accelerating at the same rate as the elevator if it's inside the elevator? I'm not going to find the acceleration of the elevator. You know what I'm going to find? The acceleration of the, which is going to be the acceleration of the elevator. So I said, okay, who's winning? mg minus normal force equals ma. And I said, well, that's doable. The acceleration is going to be m 32 g 9.8 minus, I don't know the normal force, or do I? What does a scale measure? A bathroom scale, when you stand on it, what does it measure? What does it measure? Did they tell me what the scale measured? In this question, did they tell me what the scale reads? Oh, they told me the normal force. That's where the 3.24 came from. Okay? And then once you've got the 3.24, you can go back to this equation and get friction by itself, swappy dance, because there's a minus sign in front of the friction. So for D, I think big M G minus, and I shouldn't have put a little m there, I should have put a big M there. Big M A equals friction. What's big M? The mass of the elevator plus content, 725. I don't need to add the 32 because they apparently did that when they said the total mass plus contents is 725. So it'll be 725 times 9.8 minus 725 times my answer from C. That equals friction. In fact, now I could probably even maybe figure out coefficient of friction or something like that. I needed to. A mu. Is that all right? Okay. We're going to continue on with many body problems today, looking at a very specific example. The Atwood machine. An Atwood machine is a pulley system as seen below, or if you look up, this is an Atwood machine. Sorry for those of you at YouTube who can't see what I'm doing. Basically, it's two masses connected by a string. When one goes down, the other one goes up. Although, to make the physics nice, we're going to pretend the string has no mass. Because in real life, if this was like a massive elevator cable, as this went down, the overall mass on that side would be increasing, and that's a changing mass, and we can't deal with that. And we're going to pretend that the pulley that the rope runs through has no mass and no friction, so we ignore that in our free body diagram. An Atwood machine, then, is a pulley system as seen below. The mass M2 makes it easier for a person or a motor to lift the mass M1. In fact, M2 is often called a counterweight. Oh, we have a thought problem. We're going to vote. Here's our first thought problem. It says this. Suppose equal masses are placed on both sides of the Atwood machine. I'll demonstrate it here because these are equal masses. And one mass is lifted higher. When the higher mass is released, how does the system move? Option number A, the system remains at rest, nothing happens. Option B, the higher mass falls down because, gravity. Or option C, the higher mass goes higher when you let it go. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So you got the argument. We got two identical masses. Now, again, imagine that this pulley here has no friction and no inertia. It's a magic pulley, so it's not part of the question. All right. Let's see. Who says it's obviously A, Mr. Dewick? A. The system remains at rest. A. 1, 2, 3, 4. I got a 5. Was that a twitch? Nope. I got 5. Who says, nah, the higher mass is going to fall down? Gravity. B. Gravity. Here. Who says, no, when you let it go, the higher mass is going to go higher? Oh, he is voting there. I thought for a second there he was wimping out. 18. I'm not going to tell you the answer. We're going to derive it. Do you know what this might be a good job for? Okay. I'm going to zoom in. In fact, I think I can zoom into 300. Oh, not that much. Right here. On this diagram right here. What are the forces on this left-hand mass? Get the obvious one. Okay. Label that with an mg. What else? Is there a rope? So? Is there a normal force? Are we sitting on a surface? Okay. What about on the right-hand side? What are the forces acting on it? Get the obvious one. Now, normally I would call one mass M1 and the other mass M2, but does the question say both masses are the same? Then I'm just going to use M for both of them because lazy. What else? Tension. Most of you went with answer C. So I guess if you're thinking the higher mass goes higher, you're saying it's going to accelerate in that direction. So you're arguing that that there must be the winner. That's the only way I can come to answer C. Let's try that. I hear a few people gasping like they're doing some of the math in their head. Cool. So if I write an equation, it would be this. Who's winning? mg. And then, again, I'm going to walk along the rope. Okay? So anything that ends up pointing down, once it gets to the right-hand side, is going to be winner plus. This tension, winner or loser? Loser minus. Now, this tension here, you might be tempted, Hannah, to say, well, it's pointing up, so it's also a loser. But if you follow it, when it gets to this side, I think it ends up pointing down. I think it's winner plus. And this mg here, you might be tempted to say, well, it's pointing down like that mg, so it's a winner. But again, Sarah, if you follow it, I think once it gets to this side, I think it's pointing up. I think it's a loser minus. And that equals m all A, because there's more than one mass. Oh. Hey, everybody, why am I stretching? Oh, we're losing tension again? Excellent. Ah! Why am I stressed again? What else am I losing? I get this. Well, Shea's theorem, get the A by itself. What's 0 divided by a number? Yeah. Can't divide by 0, but you can divide 0 by something. So if the acceleration is 0 meters per second squared, what's the only correct answer? And where it says, using principles of physics, explain your answer, I did. In fact, that's our first, probably in this unit, proof. Did we use any English? No, we did a purely algebraic, no numbers, proof. Now, by the way, an acceleration of 0 means either it's going to stay at rest, or if I had it moving at a constant speed and let it go, it would just keep going at a constant speed. This right here is really important. Almost every elevator that you've been on has a setup like this. Somewhere in the machinery that you can't see, there's another mass, a counterweight, that's the same mass as an empty car. And so once an elevator lifts you up, let's say, Braden, to the 13th floor, once everyone gets off, the elevator is not having to use any energy or electricity to keep that elevator car sitting up there. Everything can just shut down and remain at rest. Otherwise, we would have to still be expending energy to hold it there. In fact, any elevator, all it's lifting is the mass of the contents of the car. It's not having to lift or accelerate the mass of the car itself. It's a very clever system. Lets you use a way, way smaller motor and smaller, so you got to use same size cables because the tension is lifting the mass of the whole elevator, but the motor itself for the acceleration, not a problem. Yeah? As long as because the counterweight is the same mass, well, I guess weight, as an empty car. Yeah, because it would be the same mg as an empty car. In real life, those cables have a lot of mass. So in real life, the engine is also having to. So if you're on like the 30th floor, that's 30 floors of cable on one side. That's not balanced. We're having to take care of that still, but it's still much more efficient. Yeah. I like example 2. You know what? Example 2, will you marry me? There's going to be an Atwood machine on your test. I'll even tell you what I'm going to ask you to find, the acceleration and the tension. Part A says write force equations. I'm not going to give you that as instructions. I'm going to expect you to clue in. I probably got to write an equation to solve this, but here, we're walking you through it. So M1 is 1.2 kilograms. M2 is 3.8 kilograms. Okay. Write force equations. What I'm really saying is this is a job for a... Although, did they give me a picture? I'm going to label the picture. What are the forces on M2? Get the obvious one. I'm going to call that, this time they got the M2 on the left, so I'll call that, okay, M2G. What else? Tension? Anything else? Is there a normal force? No. By the way, in Physics 12, I give you all a question, I think it's in Physics 12, where we have M1 sitting on a table, and so M1 also has a normal force. No problem. Just means your equation is a little longer. Still winner minus loser. What are the forces acting on M1? Get the obvious one. What else? Tension. How big is mass 2 in kilograms? The question tells me. 3.2. How big is mass 1 in kilograms? The question tells me. Which mass is going to accelerate down? Which mass is going to accelerate up? The heavier mass. Is that fair to expect you to realize, I think? Okay. So I usually, somewhere on the Atwood machine, draw a little arrow off to the side with an A for acceleration. So I say that's the winner. Anything that ends up pointing down once it gets to the left-hand side, winner plus. And now let's write our equation. So I'm going to start right here. It's going to be winner. Oh, hang on. Let's part B. It wants actually part A wants just the force equation. So let's write the equation. Winner. This tension here, winner or loser? Loser. And again, you might be tempted to make this other tension a loser because it's pointing up. But Donald, if you follow it, when it gets to this side, I think it's pointing down. I think it's a winner plus. And this M1G, you might be tempted, Karen, to let it be a winner plus because it's pointing down. But if you follow it, I think when it gets to this side, it ends up pointing up. It's a loser minus. Have I gone all the way along the rope? Yep, so equals. Have I got forces from more than one mass? M all A. Oh. Losing tension. Gotta like that. Shea, what does B want me to find? How would I do that? Come on, you know you want to say Shea's theorem. Come on, you know you want to own it and just say, why, Mr. Dewick, you would use the theorem named after... Come on. What theorem would I use, Shea? Oh, isn't that great? So, going to divide by M all. I'll get this. A equals... M all is M1 plus M2, and I'll have M2G minus M1G. Now it's plug and chug. The acceleration is going to be, what was M2? I've scrolled down, 3.8 times 9.8 minus 1.2 times 9.8, all divided by 3.8 plus 1.2. I might be able to do this in my head. I wonder. 3.8 minus 1.2 is 2.6. Yeah. No. Do you get 5.096? Or am I wrong? I might be wrong. I might have made a typo. Is that right? Okay. Built-in error check. If I cut that rope right there, what's the fastest the acceleration could be? Okay. Also, nope, I'll go into that rant a little bit later. So I'm going to write 5.096, and then I'll write next to it 5.1 meters per second squared. But I'll use that 5.096 if I need to for other stuff. What other stuff? Claire, what's C want me to find? Okay, here's the nice thing. Doesn't matter which mass you use. I'm looking at both of them. Is any one of them more cluttered than the other one? Which mass do you want to use to find tension? Remember, to find an individual force, we look at an individual mass. Oh, why can't I use this equation to find tension? A tension deficit disorder. Yes. Okay. Which one do you want to use, M2 or M1? Okay. I probably, because I'm really lazy, might have used M1 only because tension's the winner and it's slightly easier to get the tension by itself. But no matter what, we're doing most of this in our head anyways, so I'm okay with that too. So you said I'm going to use M2 minus tension equals M2A, not M all A. We're just writing an equation for M2. Claire, what's right in front of the T that I don't like? So, swappy dance. M2G minus M2A, that equals tension. 3.8 times 9.8 minus 3.8 times 5.096, or use your answer button. And I got 17.8752. I'll write that as, I should check, is that right? Yeah. I'll write it as 17.9. And just for the record, if I had used mass 1, you don't need to write this down if you don't want to, but if I had used the right-hand mass, it would be tension minus M1G equals M1A. Claire, how would I get that T by itself? I minus the M1G over? I think I'd add the M1G. So if I go M1A plus M1G, notice if I do that, I get 1.2 times 5.096 plus 1.2 times 9.8. And I get bang on exactly the same to 6 sig figs of accuracy. Doesn't matter which one you use. Same diff. Use whichever one is least cluttered. Here it's a cluttered tie, so who cares? Example 3. Xavier, did I tell you there's going to be an Atwood machine in your future? Did I say I like this question? So here's what I'm going to say. I'm going to do example 3 on my own. You try this on your own. I won't say anything. I'll keep my screen unfrozen, so if you get stuck, look up. But try finding the acceleration. In fact, you know what? Let's do this. Let's call that part A, and let's call tension part B, just so we have some clear organization. Solve this. What's frozen? No, I'm not going to freeze the screen. Normally I would freeze the screen or make it blank or something, but this time you can look up if you're stuck. How many of you got that? Okay. So I'm going to say, hopefully, that's as close to free marks on your test as it, And I would make this worth a fair bit of marks because look at how many steps it is, right? 1, 2, 3, 4, 5, 6. I'd probably make this worth 5 marks. So hopefully it's like, as long as you're meticulous and careful, not too bad. Put your pencils down, look up. I like example 5. I like example 5. I like example 5. Example 5 is a nice question. Ooh. Naomi, what are they asking us to find in example 5? No, read carefully. This is what I call a missing mass question. Now we've reached the point where I can completely reverse engineer a question with you. Up till now, Donald, I've been giving you both masses and saying, find the acceleration, find the tension. Now I'm going to argue I can give you one mass and then one of either the acceleration or the tension, and you can find the other mass. And we're going to do this Atwood machine in the opposite order that we did before. Instead of looking at both masses and writing an equation for everything, we're going to start with one mass. Which mass? The one that we know. Naomi, which mass do I know? M1. Let's write a free body diagram for M1. What are the forces acting on it? Get the obvious one. What else? Okay. I'm staying away from M2 right now because I don't know it. If I tried writing an equation for everything, I'd have more than one unknown in the equation for everything. So, I have to tell you which way we're accelerating for you to find the missing mass. Which way is M1 accelerating? Say it again, you're right. Which way is it accelerating? Who's winning? Tension. Who's losing? So, even though they asked me to find M2, I ignore it. I start with M1, the mass that I do know. Tension minus M1G equals M1A. What if M1 was accelerating down? M1G minus tension equals M1A. And I will either give you the tension and you can find the acceleration, or I'll give you the acceleration and you can find the tension. We start there. We find everything we can from the mass that we know. Here it says, it gave me the tension. I'm going to find A, Shea's theorem. A is going to be tension minus M1G all over M1. And I'm writing out more of my steps because it's a tricky question. I used to only do this in Physics 12, but I moved this to Physics 11 a couple of years ago. Naomi, what was tension? What was M1? 9.8 minus 3.2. What's the acceleration? 25.1. Can't be 25 because it's got to be less than 9.8. I don't know, but I'm just telling you it's got to be less than 9.8 because if I cut the rope. Anyways. Do y'all get 7.85625? I'm going to write down every sig fig because they didn't say find A. They want me to find M2, the mystery mass, and I'm going to use this. So 7.85625. I know we haven't even started the question yet. Well, we have. We've said, look, if you want me to find a mystery mass, stop. I'm going to go look at the other mass first and find either tension or acceleration. I'll give you the other one. What was this question you want me to find? Let's write a free body diagram for M2. What are the forces acting on M2? Get the obvious one. What else? Let's write an equation for M2. Which way is M2 accelerating? Who's winning? Who's losing? What's that going to equal? Not M all A, M2A, because we're just writing an equation for M2. Naomi, what am I trying to find? How many M2s do I have in this equation? How many would I prefer? 1. How many do I have? You know what? Let's get them to the same side. I'm going to swappy dance. I'm going to get tension over there and M2A here. If I do that, I'll have M2G minus M2A equals tension. What am I trying to find, Naomi? How many M2s do I have? How many would I prefer? You know, it'd be really cool. It would be really cool if there was a Math 9 operation that I could pull out of my back pocket and change this from 2 M2s into 1 M2. And there is. Anybody see it? This is also really handy to have in your back pocket for pre-calculus 11 and pre-calculus 12. Trust me, this little trick I'm about to show you. What? Is there an M2 in the first term? Is there an M2 in the second term? Is there a greatest common factor, a GCF? You mean Math 9 is actually useful, Mr. Dewick? See, if I do that, then I can write this as M2 bracket G minus A equals T. Naomi, what am I trying to get by itself? How many M2s do I have now? Woohoo! How would I get the M2 by itself? How will I move the bracket over? What's the bracket doing to the M2? Multiplying, so how will I move the bracket over? Oh, that is so nice. Isn't that neat? What was tension? They told me 56.5. G 9.8 minus what was 8? That's why I had to find it. 7.8562, 7.85625. I think I can use my answer button. Definitely brackets around the bottom here, although I don't need brackets around the top here. You get 29.1 kilograms. $29.1 kilograms. That's a missing mass question. You're going to start with the mass that you know, write an equation for that. I'll either, Jordan, give you T or I'll give you acceleration. Find the other one. Then write an equation for the mass that you don't know. If there's 2 M1s or if there's 2 M2s, get them to the same side. GCF, now there's only 1 M1 or M2. Hey, Math 9 useful. Who knew? Okay. Last one. Given that M2 equals 4.3 kilograms and it's accelerating downwards, find A, the tension, and then B, M1. Okay. Not going to write an equation for everything. By the way, if I tried finding a tension with an equation for everything, why wouldn't that work? Because the tensions would all cancel anyways. So which mass do I know? M2, free body diagram. M2G, tension. Which way is mass 2 accelerating? So I'll even make a little note, A. It's that way. Okay. Sarah, looking at mass 2, if mass 2 is accelerating down, who's winning? Who's losing? Equals M2A, because we're looking at one mass. What's right in front of the T that I don't like? Swappy dance, right? Because A wants me to find T. So plus the T over there, minus the A, M2A there, and I'll get this. M2G minus M2A. And Sarah, do you mind? I'm going to put the T equals on that side because that's where I like it. M2 is 4.3. 9.8 minus 4.3, 2.5. Sarah, did you get 31.39? Oh, you're still typing? Okay. Is it 31.39? People nodding? Cool. I'll write 31.4, but I'll keep that 31.39 on my calculator. Is that okay, Caleb? Thumbs up. Caleb, what does B want me to find? Which way is M1 accelerating? Because M2 is accelerating down. Okay, quick free body diagram. M1G tension. So let's find M1. Just going to write an equation for this one. Who's winning? M1G? Because it's accelerating down? Which way is it accelerating? If it's accelerating up, tension's winning, like you're feeling right now. Minus M1G, and that equals M1A. Caleb, how many M1s do I have? How many would I prefer? Get into the same side. I think here it's not going to be a swappy dance. I'm just going to plus the M1G to that side. And I'll get tension equals M1A plus M1G. How many M1s do I have? How many would I prefer? You know, it'd be really cool. It'd be really cool if it was a Math 9 operation that I could pull out of my back pocket and change this from 2 M1s into 1 M1. Is there one? Yeah. What? No way. So you're saying I can write this as T equals factor in M1 out and I'll get A plus G in brackets? Oh. How would I get the M1 by itself? What's the bracket doing to the M1? So you're telling me M1 is going to be T all over A plus G? I think so. It's going to be, what was tension? 31.39. All over, I must have told you A, 2.5 plus 9.8. And I get 2.55 kilograms. Good stretch? Losing tension? Yeah. What's your homework? Okay. Number 1. Number 2. Number 3. Number 7. So I skipped 4, 5, and 6. Number 8. Number 9. I skipped, so I think I assigned 1, 2, 3, skip 4, skip 5, 6, 6, skip 6, 7, 8, and 9. Put your pencils down, look up.